in Space, brought to you by Orbital Assembly Corporation, with your hosts, Dr. Jeff Greenblatt and Eric Ward.
Hello and welcome back to Our Future in Space. I'm your host, Dr. Jeff Greenblatt. I am the Vice President for Science and Research at Orbital Assembly Corporation. In this podcast, we explore the technical, economic, social, political, and ethical considerations of moving humanity into space in large numbers. Our species is at an inflection point in its evolution where we now have the ability to sustain life off-planet, so far in low Earth orbit, but soon throughout the solar system. Will we merely survive or expand outwards and thrive?
Orbital Assembly is leading the way in the development of artificial gravity stations so people can live, work, and thrive in space.
OAC's platforms are market category creators. They are backwards compatible with current standards, allowing for you to move from concept to production at the pace of business.
To learn more, visit orbitalassembly.com.
All right, I am joined today with my co-host, Eric Ward, the Vice President for Engineering Design at OAC. How are you doing today, Eric?
I'm doing quite well. I'm looking forward to this one. We have Dr. Martinelvis back on the show. For those of you who didn't see the first one or don't remember, Dr. Martinelvis is an astrophysicist at the Center for Astrophysics at Harvard University and Smithsonian Institution. Martin has published over 400 papers on supermassive black holes, which we see as quasars. He's a fellow of the American Association for the Advancement of Science, a member of the Aspen Center for Physics, and is past chair of the Hubble Space Telescope Users Committee and of the High Energy Division of the American Astronomical Society. Concerned about the future of astronomy, he has turned his research to asteroid mining, covering both technical and legal policy issues. Asteroid 9283 Martinelvis is named after him, and he's the author of Asteroids: How Love, Fear, and Greed Will Determine Our Future in Space from Yale University Press. Dr. Martinelvis, thank you so much for joining us again.
Hi, it's a pleasure. I realize we've got the same Our Future in Space tag on our show and book.
All right.
Yeah, absolutely. So what have you been up to since we talked last some months ago?
Well, I've since getting the book out, I've moved on to more immediate things, which is the moon, and I've been doing a lot of things about, for instance, where are you going to put astronomical telescopes on the moon? And it turns out, as with everything else, some places are far better than others, and so we need to protect those sites. And I've been working on that.
Wow, I'd love to talk to you about that in an upcoming episode as well.
We can do that.
Yeah, absolutely. But I think, what is particularly relevant now is to talk about NASA's DART mission.
Oh, yeah.
That's the Dual Asteroid Redirect Test, DART. And we wanted, you to kind of leverage your expertise in asteroids and tell us a little bit about this mission. Here on September 26th, I believe DART is gonna do an impact. So why don't you tell us a little bit about this mission and kind of where it came from and what the goals are?
Okay, well, the goal is to, for the very first time, deliberately alter the orbit of a solar system body. Right? We've done it in the past by accident, by deep impact and other things, but this is a deliberate aiming to change the orbit of this small asteroid. What we're doing is changing the orbit of an asteroid that's that's gravitationally bound to another one. It's a moon itself of a bigger asteroid, and that's really helpful because it enables us to tell exactly how much we changed its orbit.
Yeah, and what I have up here right now, Martin, is a diagram showing the orbit of Dimorphos, the little moon around Didymos, which is the asteroid that DART is currently heading toward. Anything else you want to mention based on this diagram?
Well, I see the Chia cube, which is an Italian CubeSat on the picture, and that's just been deployed and is going to watch the impact from about 1,000 kilometers away. And then a few minutes later, from about 50 kilometers away, it's going to take some detailed pictures trying to see the plume of debris and see if you can see the impact crater and that kind of stuff. So Italians are very pleased about this because their very first Italy-only deep space mission. So another country is joining the deep space exploration.
Excellent. Well, congratulations to them. That's wonderful. So it looks like what we're doing here is not changing the orbit of an asteroid around the sun, but we're changing the orbit of this asteroid moon, Dimorphos, around the main asteroid Didymos,
Right.
but not, its relationship to Earth or the sun or anything like that. Is that right?
Yeah, and that's good. It's a very safe thing to do. In fact, it's changing by such a small amount, because what we're doing is hitting it with the biggest mass we can at the highest speed we can, because that imparts the most momentum, as we call it. And when we hit the asteroid, it's bound to slow down by that much, by the relevant amount, which is a tiny amount, by the way. The speed the change in speed for this little moon, Dimorphos, is less than the speed at which a snail can move. So you're not making much of a difference, but you are making some.
Oh my
And
God.
the idea is to see how much we do slow it down. And you might have thought, well, we don't need to test that, because conservation of momentum, we know we hit it with this much momentum, it will lose that much momentum, so it's not an issue. But that's got an assumption in it, and that is that you don't kick up any debris when you hit the asteroid. If you pick up a lot of debris that moves out in the opposite, back along the path of the impactor, then that changes the momentum equation, and we want to know how big that multiplier is. Do we win a lot or not? Because you really don't want to be surprised when you need to do this for real.
Now, what might we want to do this for real? I mean, let's get to the point of why we're doing this mission at all. What's the bigger picture here that we're trying to understand?
Well, this is grown out of a whole series of discussions about planetary defense, and there are actually conferences called the Planetary Defense Conference every couple of years in interesting places. And what we're defending against is killer asteroids that would come and not wipe us out the way the dinosaurs got wiped out by a really large asteroid. Mostly we're not worried about that, because we found 90% of the possible giant dinosaur killer asteroids. So we'd love to find the rest, and it's going to happen. But it's more the smaller ones, and they come by much more often. So I think you have a plot of how often different size asteroids come by.
Yeah, right here. We're showing a diagram of, it's called the hazards by the numbers. Go ahead. Yeah.
We see the 4-meter ones, they come by very, very often, but they burn up in the atmosphere, and it doesn't matter. 25 meters, on the other hand, that's about the size of the one. It's a little bit bigger than the one that was exploded over Chelyabinsk a few years ago. And
it looks like we estimate around 5 million of those in our solar system, and we have discovered about 0.4% of them.
Yeah, we're a little lagging behind on that, but there are two big surveys, which I could get to now or later, that are coming along in the next decade that are going to change that picture a lot. Especially as you get, certainly for the bigger ones, 140 meters, that's going to be essentially complete. Everything about that. It's going to be a bit spottier at 25 meters.
Well, maybe you can tell us about that in a moment. But first, I want to just interrupt our broadcast to play one more short ad here, and then we'll be right back with Martinelvis. Hang on a second. Okay.
Ideas are powerful things. Ideas drive us to broaden our minds and help us seek truth about the universe around us. We are Rogue Space Systems. Ideas above.
Right.
Okay.
So tell us about those upcoming surveys that might help us find, I guess, the rest of these potentially hazardous asteroids, at least in that kind of 140 meter class, which is sort of the city destroying size.
Yeah, they're pretty big. Though that could even do a regional damage, I think. But so there are two surveys. One is taking an ordinary ground-based telescope on a mountaintop, which is carefully designed to look over a very wide field of view. Most telescopes for astronomers, the professional ones, look at a very small piece of sky. This is designed deliberately to look at a big piece of sky, so you can cover the entire sky that's visible each night, every night, which has never been done before, not nowhere near this depth. And so they'll take pairs of images, and you'll see moving objects in there, and that will pick out any asteroids that are in that field of view in the sky every night in that night, and it's going to go on for 10 years. And so almost everything that's in a near Earth orbit will pass by during that 10 years. So it's going to be very complete. And for that, it's going to be limited in one way, though, and that is it won't see the very dark asteroids, very low albedo, low reflectance objects. So what we're seeing in optical light is just reflected sunlight. And that there's so many asteroids out there, particularly the carbonaceous ones, the C-type asteroids, that are darker than fresh asphalt, darker than a blackboard. And so they reflect a very small amount, a few percent of the light that sunlight gives them. They're hard to find this way. So we're going to be a little biased against those, and they could be very numerous. So
I was going to ask, how many do we think out of the total there are, so that we know what our blind spot is?
Because they're so hard to find, that numbers are pretty uncertain.
Right. But is there not a way to find those dark asteroids more easily using infrared?
Absolutely, that's the right way. So these, because they're near Earth asteroids, we know their temperature is going to be similar to that of Earth, about 300 Kelvin. And so the radiation they emit just for being hot, the black body radiation, that will peak at a ray in the infrared at a wavelength of 5 or 10 microns. And there is a mission that NASA has got started called the Near Earth Object Surveyor, and that they're planning to launch originally in 2026, but there may be a bit of a funding issue. 2028 might go to, and I hope not. It'd be nice to have it quicker and very much at the same time as the Rubin Observatory, which is the optical telescope I was talking about. And that will see all the dark ones very easily, because they'll be glowing. All that absorbs sunlight gets turned into heat and warms up the asteroid, and it glows. So in that light, and it's very easy. Once you've got your 10 micron telescope up in orbit, you have to do it from orbit, because the sky is very bright. It's the same temperature as the asteroids that you're looking for. So it's very hard to see. The bright sky is bright on Earth at that wavelength. If you go above the atmosphere, it's all gone. So it's an enormous gain, factors of many.
Well, it sounds like that's definitely the way to go. And I mean, I'm kind of surprised that there's funding issues with these sorts of satellites, because this is something that's going to protect all of humanity, not just the United States.
I don't know who was against it, but they didn't come fare well in the budget process. So there are moves in Congress to restore the funding, but I don't know how successful they'll be. I hope they'll be successful.
So you mentioned near Earth asteroids, and these are the ones that are potentially hazardous. Could you tell the audience a little bit about how these are different than the main belt asteroids, and what usually people think of when we talk about asteroids?
Oh yeah, sure. Indeed, by vast numbers, the main belt between Mars and Jupiter, the orbits of Mars and Jupiter, is where the bulk of the asteroids are, both in number and in mass. But every so often, these asteroids get tugged by the gravity of Jupiter, and they change their orbit slightly over time, and they also get they can actually change their orbits just by being illuminated by the sunlight as they turn, and so their orbits are always slightly changing. And if they stray into a resonance with Jupiter, so then they get a kick every time they go past Jupiter, and this changes their orbit much more radically, and will move them into many of them into orbits that come into the inner solar system, past the Earth. And
so essentially, you're saying that they're even though most of the asteroids in the solar system are in the main belt, they're enough to get sort of nudged by Jupiter or other effects closer to Earth on a regular basis. So it's kind of like there's a trickle, a constant trickle into our orbit.
Yeah, it's a concentrical into our orbit, and they don't last all that long in astronomical terms, a million years, a few million years, and then they keep, their orbits are changed again and they move out. But the new ones come in, so it's a flow, and they're mostly smaller ones because they're more common anyway out in the main belt, and so they're more likely to be the ones that get kicked in.
Okay, but there is a significant hazard. I mean, if
there's probably 20,000 of them, big enough, as big as 100 meters across. So football stadium size.
Right.
So you don't only a small number of those actually have very close passages to Earth, right? So those are the ones we most care about.
Right, but we don't want to roll the dice. We still like to reduce that to zero, right?
This is one of those. It's one of the few existential risks, perhaps the only one to humanity, which can actually be eliminated, because we can find them all, we can track them all, and then if any of them are dangerous, and even 100 years from now, we can change their orbits. At least we will if Didymos, I've forgotten the name, Dimorphos it changes its orbit as we hope it will, and it really has to. So we're going to.
So what?
Go ahead, Eric.
I was going to ask, it sounds like you mentioned that, if it changes like we thought, what are the factors there that are making this questionable, right? Like if I knock two billiards against each other, I know exactly which direction they're going to move in afterwards based on their mass and their speed. Can you get a little into more details on what that question is and why we're not sure what'll happen?
Well, there's several things. One, as I mentioned, is if you're kicking up a lot of dirt and it goes backwards, that will increase the transfer of momentum. And we just like to know how much that is. But the other worry is that asteroids are made of, many of them, of just rubble, right? And in zero gravity, rubble behaves differently. And there are very few experiments on this, but there are a couple that show that rubble is very different. It's called a granular material, and the whole subject is called granular physics. And you remember that OSIRIS-REx picked up a sample from the asteroid Bennu, and what isn't said too much, but it was quite shocking at the time. It came in slowly, trying to land on the surface and grab something, and we actually landed on the surface and blew gas out that would then make the rubble go up into a collection device. But as it came in slowly, it just kept going, as though the surface wasn't really there, right? And that is one of the strange properties of granular material in zero G. It just doesn't resist like that. You just go through it as though it's a knife through butter.
So it's kind of like knife through butter, or sort of a big pile of fluffy flour or something, right?
Yes, if you hit it hard, it behaves more like you would expect. But then what happens is shock waves go through the asteroid, and you might find it more like Newton's cradle, kicking something off the back end.
I see.
And of course, the third thing is it might just start falling apart. If you hit it with enough energy, the whole asteroid might start to disperse.
So that was the question I was getting to, is that if you're dealing with a large and therefore potentially hazardous asteroid, but it's made of this really fluffy, unconsolidated stuff, so that essentially you're saying you can't hit it with a kinetic impact like the DART mission. What other, I mean, first of all, am I correct in that? And what options do
we don't know, right? That's why you have to do the test. You see what happens. Yeah. Probably the amount of energy that DART is going to impart into this body is too small to disrupt it. But we have to see.
Well, kind of along those lines, actually, a friend of the show, Aiden, just asked, which event would be more of a hazard to Earth? One large asteroid strike or many small asteroid strikes?
At the same time.
Well, Earth itself will be just fine, thank you. We might have problems, and of course, the once every few million years cataclysmic event from a kilometer size or several kilometer size asteroid would be more of a problem when it happens, because it could wipe us out. It would certainly wipe out any civilization. So yes, but that's those I think I'm confident we'll be able to find and track
Mhm.
very soon. Within 10 years, we'll know where they all are.
Yeah.
And let's hope one doesn't turn up in the meantime, because it's always statistical. It's once in a million years, but that could still be tomorrow, you know.
Yeah. Yeah.
Yeah. Well, I still want to press you for, so if we detect a really big asteroid, and I'm going to bring up this image of, Didymos and Dimorphos again. If Didymos, which is almost a kilometer across, were somehow to get on a direct collision course with Earth, and I'm thinking this is about the size that was portrayed dramatically in the movie Don't Look Up that many of us may have seen the last few months. How could we avoid this impact? I mean, the little impact from the DART spacecraft is not going to be nearly enough to push it off course, right?
Correct.
So what would we do?
We have, it depends how much warning we get, right?
Okay.
And whether we decide to take action about it, because that was the whole "Don't Look Up" premise. That,
Right. We kept delaying.
Yes, but but we don't want to scare anyone, so let's not do anything. It might be not be good for my re-election, as opposed to there not being any re-election because there's no one to vote.
Right.
Right. Kind of makes it not obvious. But seriously, I mean, just to get on to the topic of, could we just build a bigger spacecraft and impact it, or do we have to switch to other techniques altogether for something that size?
Right. Well, there are several other techniques being mentioned. So what we've talked about just now is like a hammer blow. There's also tractors, there's nukes, and there's billiards. That's how I like to put it. And so let's see, the nukes are easy to understand, because if you explode a nuclear bomb just as you touch the asteroid, or just preferably a millisecond later when you're in a little bit of a dip, a little created crater, that will impart a huge fraction of its energy to the asteroid, of its momentum to the asteroid, and that will that works much better because you've got an awful lot of energy there. So that scales us up somewhat. Whether that could cope with a kilometer-sized object, I don't know. Of course, it all depends on how soon we get to it, as I was saying. If you've got a long time, a year's warning or a few years warning, then a small change in the velocity of the asteroid will add up over that time and make it miss the Earth. If it's a week away, yeah.
Right. So that hence the need to identify these when they're still far from the Earth. And therefore,
yes, very important to do.
Right.
So the other things you can do is, if you've got like 20 years of warning, is just go there with a massive spacecraft. Don't hit it, but park your spacecraft either in front or behind of it, depending on whether you feel like pulling it or dragging it, and let gravity do the work. Then, of course, if you don't do anything, they'll collide. So you have to have jets on your spacecraft that's doing the pulling that keep the spacecraft at the right distance. And of course, those jets shouldn't point at the asteroid, because then you're not doing anything.
It's like using a fan to blow on your sail to make your boat go faster.
Exactly.
Right.
It works in the cartoons.
Yeah, right. I saw Wile E. Coyote do that once, so maybe it'll work.
That will work in real life.
That's slow, because we can only launch a few tons of spacecraft. So another idea is to go to the asteroid that's dangerous with this spacecraft, and with a big hook, and pick up some giant boulder from the surface with a mass of many tons, and then maybe 10 times as much as your spacecraft, and then you can speed the whole thing up by a factor of 10, and so it goes from maybe a 20-year lead to a 2-year lead, and that's great. It's an embarrassing notion that you get to this asteroid and it doesn't have any big rocks to pick up, and you say, "Oh, my bad, we're all going to die."
And then we don't have enough time to disrupt it. We definitely don't want to be in that situation. But I have to ask you one other question, Martin, about I don't want to focus too much on this Hollywood movie, Don't Look Up, but I think it was made partly to raise awareness of the potential for asteroid impacts and perhaps other things we worry about too. But in that movie, they talked about the opportunity for mining the asteroid for profit as kind of getting in the way of moving it out of the way of a collision. I'm just wondering, how real is the prospect that a potentially hazardous asteroid could actually be of economic value, assuming it doesn't hit Earth, that is. Is there kind of a double-edged sword or a win-win, I guess?
Maybe. I mean, I'd have thought the right argument is we want to deflect it and put it in orbit around the Earth so that we can then mine it easily. That would be the sensible thing to do if you could do it. Well, the chance of it being what do we want to mine, right? And it would be material. There's nothing really that you can mine in space that you would want to bring to the ground that you could plausibly do profitably. Now, it might change if you manage to put one of the killer asteroid in orbit around the Earth, because that's relatively easy to get to. So the only things you might bring down are platinum group metals, because they're worth $50 million a ton, something like that. But I think mining it to build things in space makes a lot more sense.
Yeah.
So if it was a metal asteroid, pure nickel iron, then it'd be great raw material for building, I don't know, giant artificial gravity space stations, for example.
Yeah, perhaps.
Wouldn't that be handy?
An idea.
Yeah. Only really big.
Yeah.
Oh, sure. Now we're talking.
We have that much.
Right. Because it overcomes one of the real problems of getting that much mass to orbit.
Yeah, for sure.
And how nice if there's an asteroid that is sort of on its way to us already, so we don't have to spend as much energy moving it into a convenient location.
Saves a lot on packaging postage.
Yeah, definitely.
Well, yeah, we're getting close on time here. I know you've got another meeting, and we wanted to keep this interview pretty focused on the DART mission. If listeners are interested in learning more about it, do you know of any good resource to learn about the DART mission in particular? Maybe watch it live or learn about just asteroids and potentially hazardous asteroids in general?
Well, I'm sure that the NASA websites are very good, and I'm sure there's an Italian ASI website that's going to be very good too. But that may be in Italian. You never know. Yeah. Of course, a fine discussion of this whole thing is in this book.
Asteroids.
Yeah, I think we might have seen that one before.
Yeah. So I talk about the DART mission in there and give lots of these numbers and a lot of background.
Yep. So, I've read through that book. I recommend it to our listeners too. If you want an interesting read about asteroids, it's very well written. So
yes, I enjoyed it as well.
Yeah.
So.
2 readers.
Yeah, you did it. Excellent. Well, thank you so much for joining us. If you're listening and you want to watch the DART Impact Live, if you catch us in time, we'll put a link in the description for this video and podcast with the NASA TV link on YouTube. I believe they're going to be streaming that live. So you can, watch and follow along. So thank you so much for listening. And again, Dr. Martinelvis, thank you for joining us and helping us and our listeners learn more about space. So if you're listening and you have any suggestions or you'd like to get on the list to watch these recordings live, please reach out to us. You can send us an email if you're old-fashioned, ourfutureinspace@orbitalassembly.com. You can also find us on Twitter @OurFutureSpace and Facebook @OurFutureInSpace. So thank you so much for listening and thank you for joining us.
And if you would like to find out how you can get more involved, helping support the work that OAC is involved in, feel free to reach out to us at info@orbitalassembly.com for more information. Thanks all for listening. Till next time. Bye-bye.
This program represents the personal opinions of the hosts and their guests. The content, opinions, and views do not necessarily represent the views and opinions of Orbital Assembly Corporation, nor the organizations with which any of the program participants may be affiliated. The mere appearance or promotion of this program does not constitute an endorsement by Orbital Assembly Corporation or its affiliates. Our Future in Space. Copyright 2022 Orbital Assembly Corporation. Hosts Dr. Jeff Greenblatt and Eric Ward. Audio and video production by Tim Alatorre. Musical theme The Last Day by Dark Blue Studio.